Hi everyone, today we'll continue our first simple single neural network project. It's time to code what we talked about in the previous video. I have written up all of this as an article on my website, so you can actually go to zerobyte.io. Well, basically there's only one there's only one article there for now, so it's going to be very easy to find. And you can access code snippets here, so you can just copy paste some stuff. You're free to do so. We plan to write two scripts. One is going to be training script, and the other one basically it will be an inference code. Okay, let's just start. Let's create new file. Let's create train.py. So this is going to be our training code. I'll be using NVim for this. It's very simple code, so you can basically use any code editor you are comfortable with. And we'll use only one library. This is a built-in library. It's a math library. So let's also get rid of this boilerplate. This is going to be our entry point. Main. Okay. Main. Let's also define the main function. Cool. So we already know what kind of variables we need because we talked about it in the previous video. So at this point, I'll just copy these to our script, and there we have it. As you see, we defined wseed as a list that holds initial values for our weights. So we're gonna use them for the first calculations. So let's just grab those and copy them into a new variable, right? That we'll use for calculations, and at the end, this variable will have our final weights. Next, we need to actually perform those calculations. We know the order of the computations from the previous video. We have to loop through epochs, and inside each, we have to loop through each input where we actually do calculations and update weights. So essentially, we have a nested loop, basically. Okay, so let's define that loop. So for epoch in range, and basically you could write it like this, right? It's just that by default range starts from 0 and then subtracts 1 from the provided value. So we have 1000 minus 1, right? So we will be calculating from 0 to 999. But usually you say epoch 1, epoch 2. So let's start from 1 and add 1 to our epochs. So you go from 1 to 1001, so from 1 to 1000. And so that's actually helpful because later on when you want to see which epoch you're currently training and you print epoch, you don't need to remember to plus 1 here. Actually, we forgot semicolon here. So if we run the script, actually you can't see. So you see we go to exactly to 1000, which is pretty cool. Right. So let's go back to the script. We don't need that. Oops. We don't need that. So now inside each epoch, we need to loop through each shape in our dataset. So for I in range, and let's do len dataset, right? Oops. So this gives us the number of items in our dataset, which is 5 shapes. So we are looping from 0 to 4, which are indices. We need to access each shape and its corresponding label. We could use enumerate or loop directly over the dataset, but using indices makes it easier to grab both the shape data and its label at the same position. So then we call a function that we haven't defined yet. Let's call it train step. And let's think what we have to pass to this function. So definitely we need our inputs. So data set I. Obviously we need labels, right? So we pass corresponding label as well. and we have to pass W, our weights as well. So let's assign this to W actually. So the function will perform one training step and return the updated weights. So basically we can now define this function, right? So the function will accept data, label, and weights. So we'll write the code to follow the exact same order of operations as we showed in the previous video. So it won't be the most optimized optimized code, but it's really intentional. We want to show each line to directly correspond to the equations we defined earlier, so you can clearly see each step happening one by one, just like in math. So this is also defined in the article right here. So first we calculate weighted sum. Right, and we need a sum, obviously. And inside sum, we take our data, multiply it with corresponding weight, and then for E in a range. So this is just a nifty way to write entire expression in one line. Len data, right? So what is next? So next is prediction. So basically how we're gonna write it is prediction, and so basically we take our weighted sum and run it through activation function, and we decided to go with sigmoid for this. So let's just sigmoid and weighted sum. So obviously that function needs to be defined. So we're gonna take a value, and we already described the math. So basically we're just gonna copy this. So we will return the this value. Now, the only reason we actually imported math at the beginning is just so we can exchange this this Euler number with math.exp, and here we actually we are using that x value. Oops. Okay, that's good. So we have our prediction. What is next? Error. So label minus prediction. Well, that's really easy. So that is exactly how we're gonna write it. I mean, that's it. So next we need to do adjustments. So that's learning rate times error times each pixel in our shape. So we defined learning rate as h, that's 0.1. Okay, adjustments. So here we'll be getting a new list. So definitely need a loop here. So learning rate times error times each pixel in our data, in our shape, and we need to loop it, right? So again, you can use data here, you can use W, it doesn't really matter. Both those objects have 9 elements, and that's how many times we need to loop. Weights, and then weights is weights plus adjustments. So again, new list, and then you just sum each weight with its adjustment. Right, then again, it's a loop. Right, you can just do this like that, and let's return, because that's it, and that was the last step. So we can return weights. So this goes back to our W variable, and the loop will repeat with the next shape. So this will go 5 times. We'll jump to the epoch number 2, and we'll just repeat 1,000 times. Okay, let's try to print something. Let's see if this actually works. So training complete, And well, of course, let's print the most important part of it, which is our final weights. Final weights. So let's actually add this variable, right? Cool. Let's see if this works. So we'll Python 3 train. Right. Okay. So it works. At least no mistakes made, right? So it's actually interesting to see, right? Because we actually successfully encoded our data into this kind of set of completely arbitrary numbers, right? So the next step is actually to write the inference script so we can actually see if this works. So let's create inference script. Copy weights. Create inference script. Okay. We'll import math. Let's assign weights to a new variable. We need also import. We need one library. So if you don't have Pillow, you can basically just install it by yourself, right? Just like this. So yeah, if you don't have it, just install it. We also need labels and shapes, so I'll just copy this. Obviously, no point of retyping everything. Let's just copy this as well. Right. Pillow is a library for processing images. We want to drag and drop an image into the terminal and convert it into a list of values. So basically that's what we want. And these values will represent the pixel colors of that image. So let's make a drag and drop possible. Let's define main first, and then input path. So we make the drag and drop possible by specifying input, and then let's add some prompt. Drag your image here. That's cool. So now that we've grabbed the image, let's read the pixel info. So pixels equals image. We'll define a new function that will take this input path as a parameter. Right. So let's define this function actually. Let's create a new variable image, and let's convert this image to luminance scale. So this will give us a range of black and white pixels. So image equals image open, and then that image path that we just got, and convert to luminance scale. And actually here it's supposed to be from pil. That's wrong. And I don't know why I actually put image path. It should be input path. Okay, so now that we have all this pixel information inside a variable, we can read pixel by pixel and assign 1 or 0 depending on the color of the pixel. So at the end of the day, all we want is actually a list of values like so. 1 for white pixels and 0 for black pixels. So let's return a list, and we return 1 if image get pixel at the position of x and y. So we return if the value is greater than 128, otherwise we return 0. Right, because the range of color is from 0 to 255. 0 is pure black, 255 is pure white. So everything above 128, we can safely return 1. Okay, now let's construct the loop. So for y in range, so y obviously is height. and for x in range width. So that's basically cool. So let's actually grab these height and width information. Okay, that should be fine. So actually, it seems that we should be getting what we want. So we can test it. So let's print. Maybe let's print pixels. Right. So let's run this script. Now we can drag and drop some shape. Okay, so exactly, we are getting exactly what we wanted. Right, so let's get rid of this for now. So now, more exciting part, right? Because actually we can take our data and make a prediction to actually guess what shape are we looking at. And as we already talked in the previous video, we went over this already, right? There are only like two equations that are super simple. And the reason we write those scripts the way we do, which are not the most optimal, but I want you to see the connection between those two. I want you to see we are using exactly the same math, just less actually math for inference. So we've already done this, right? So let's make a guess, a variable, and then define prediction function. And let's see. So what do we need here? So we need our pixels, like our data, right? And weights. That's it. So we just pass pixels and our weights. So let's define this function now. And this function, so pixels is our data and our weights. So basically what we can do is we can copy from the previous script, right? So we did that in a training step. We just don't need label now, but these two we can just basically copy paste. Also, we need that sigmoid function as well. So you can just take this and just copy paste. Let's just copy paste this at the top. And here we just return prediction. And that's basically it. So now we have a prediction, and now we kind of have to match what we get to our shape. That's why we have those labels. So we need to classify it. So we can actually test and see what we get. So we can print our guess. Let's see. Let's run this, and I'm gonna drag and drop L shape. And we get a prediction. So if we go and see how you label this, L shape was actually 0.75. So now it's just a matter of writing a little script that will just output the name of the shape based on this guess. So that's why we call it a classifier. So let's actually do that. Let's get rid of this. So we can now do create a variable shape and function classify, parameter guess, define classify. This is our incoming value. So basically we just need to loop through our labels and then compare it with our guess value, and based on that we will output shape name. So let's just loop through it for I in range len of labels -1. We do -1 because we are checking pairs of labels, right? So then we do if value is less than, so we need to, so we're basically gonna find the midpoint between two labels, and if our prediction falls below that midpoint, we return corresponding shape at that position. So labels I plus labels I plus 1, and we'll divide it by 2. And yeah, so we return shapes I, right? And and if we get through all the labels without returning, that means our value is like closest to the last shape. So we just return shapes -1, and this is unnecessary. Okay, which is the last. So -1. This is the last element of our shape of our shapes list. Forget to close parentheses. Right. So basically that's it. We can just print our guess, our prediction, and print the name of the shape. So print prediction guess, and let's print name of the shape as well. So that should work. Let's test it out. Let's drag a shape. Okay, so that would be it. Let's try another one just to make sure. Yep. Okay, so there you have it. Everything seems to be working. I hope this kind of explains it. Explains like the very basics of machine learning, and so you can see how these weights are adjusting during training, and then how you retrieve that information based on the input, so you can see how it works from both ways. Yeah, thank you, bye.